Hello and welcome to another video. This time we're going to be looking at an LED driver chip with an I2c connection. This particular module has an 8x8 LED matrix. On the back you can see there are some solder pads if you want to change the default address on the I2c bus. This particular chip is used for driving various different sorts of LED products, not just this 8x8 matrix, although this is quite a popular one. This chip can drive two 8x8 matrices next to each other. And if we look at how the memory is arranged, we can see that it allows for this. It has quite a strange format. Each byte we send corresponds to a vertical line of pixels. And you'll also notice that the most significant and the least significant bits are not necessarily where you might expect them to be. Not only are they reversed, but also the most significant bit has been rotated round 1 bit position. This format works quite well if you're running a display which needs scrolling text. But if we want to put ordinary binary computer graphics on this display for a game or something, then this isn't really particularly friendly for us. If we're only planning to use one display and we rotate it on its side, then the memory allocation becomes a little bit easier to deal with. In this scenario, each line going across is represented by 1 byte. That's friendly enough, but the bits aren't quite in an easy order. As we can see, the most significant bit has been rotated 1 bit position, and the order of the bits seem reversed from what we would normally like to see. We can also see that the memory location for each byte goes up 2 at a time, so that our first display that we're looking at always has an even memory address, not an odd memory address. We need to allow for this when we send data to the device. So in the code we're going to look at today, we've set up an 8-byte buffer, and this is arranged in a format that we'll be familiar with. That is, 8 bytes in each row, and with the least significant bit on the right and the most significant bit on the left. We will then deal with the rotation and the reverse order of the bits as we send each line over to the device. If we look at our code, I won't go through every routine in detail as it's well documented, but just cover some of the key points. And some of the commands are mentioned at the top here for easy reference. But one of the things we will need to do is configure the matrix. This is where the LED control chip needs to be configured before it will work. So in the configure matrix routine, we're going to send 5 bytes, and those 5 bytes are below. But we send each one at a time, not as a continuous stream. Then the device will be configured correctly. If we run the code today, what we've got is 2 routines set up. One which is going to cycle through some graphics characters, and one which will draw lots of random pixels. They're both using the same technique though. They're drawing data into a buffer, and then that buffer is being sent to the display, but converted to the right format as it goes. If I press the R key, you can see now the display is simply plotting a random pixel and unplotting a random pixel, but doing it pretty fast. In pressing G, we can go back to our graphics characters again. Escape key will quit. So looking at the 2 routines, the graphics one first, it'll just check whether any keys are being pressed and wait briefly between each different character it prints. It's then going to find the relevant data within a chunk of data that we've imported. It will put the start point of the data we want to transfer into HL. And the command set buffer data will transfer 8 bytes of data from our source into our buffer. And then the command send matrix data will send that buffer onto the LED. And we'll normally need to call update matrix to force the LED to update its display from its inbuilt memory. And this loop keeps going round and counting up 8 positions within our data so that it gets a different character each time. If we go on to the random pixel routine, the first thing we do is clear the buffer and send that data to the matrix so that the matrix's memory is clear. After checking for the key presses here to go to a different mode or to escape, we then get some random data. I'm using 2 different random number generators here to try and really mix it up so it doesn't get too repetitive. This first routine gets a random number and sets a random seed of the other routine. We call the random number generator, which gives us a number between 0 and 255. We're only interested in a number from 0 to 7 because that's the number of pixels we have. We do the same a second time, and that will give us an X and a Y position, and then we call the plot pixel routine. We then do the same thing again and call the unplot pixel. So we've plotted a random pixel and we've cleared a random pixel. We'll then send that data to the matrix and force an update on the display. As you can see, this is quite a simple module to use once it's been configured correctly. I wonder what applications you can think of to use a display like this, or what games you could create that only use 8 by 8 pixels.